Hello and welcome to another Developer Essentials. So this time around we're going to be taking a look in detail at these things called transforms. So we've used them a bit, we've worked with their position, we've worked with their scale, but we want to start diving into more detail with them. We want to start looking at some of the other things that we can be doing there with them and understanding different ways that we can set stuff up. So one of the key things I want to be looking at today is going to be working with rotations initially. So firstly, just having something rotate independently, but also having stuff where we have something looking at something else. So as always, I'm just going to get my scene set up and we'll just have the obligatory setup of we will have round, and I'm going to have a material for some cubes because we're primarily going to be using cubes today. Mostly because they are really easy to actually tell where they're moving. So that's our ground. And we'll change the color of that. Make it a darkish gray. That looks good. Set up our cube. And again, reposition that. And I'm just going to reposition that so it's a little bit up in the air. About there's pretty good. I'm going to move my camera up a bit as well and in a little bit and tilt it down. That's good. So my cube, let's give it a material as well and change the appearance of that. Excellent. Cool. So that's the first cube set up. So we're going to start to look at rotation. And then while recording this, also you might notice at times me looking over to my right. That's to make sure that this time I've actually hit the record option and haven't inadvertently stopped it while we're running. Because that is an actual thing that happened earlier today. So we've got our demo rotation script and we're going to attach this on. So we're just going to look at the simplest setup initially for doing the rotation. So we've got our rotation here, and this rotation that we're able to view in the inspector, it works in degrees. So means that 90 degrees will rotate something like that, whereas then different amounts, we can do that positive or minus. 360 degrees will rotate something fully around to the start. So if we follow sort of where the green arrow is, we can see we're at 350. If I then go to 10 more, we go back to being 360, which is the same as 0. So we're working in degrees here for the rotation. So what I want to do is I want to have this just rotate at a specific rate. So to be able to do that, I need a vector 3 because I want to be able to rotate it different amounts in different axes. So I'm going to have my rotation speed. Now the other thing I'm going to do here that we might have seen before is I can add a tooltip. Rotation speed in degrees per second. So this, by adding in that tooltip, when I go back to the inspector, not only will the variable appear here, but when I mouse over it, I get the customized information. So tooltips can be a really handy thing to add in for your public variables. Makes it really easy to know what the particular things are doing there in the inspector. In particular, if you're doing anything sort of unusual or atypical for how something is working, set up a tooltip for it. Makes the process there much easier. So I'm going to rotate using the simplest method, which is to say my transform Euler angles. I'm going to add to that my rotation speed multiplied by time, delta time. So Euler or Euler, I've heard both pronunciations. Euler's the main one I've heard, but I also am one of those probably very annoying people that alternates which one I'm saying depending on where I'm at in the conversation. So Euler angles are a way that we can indicate the rotation for something. Euler angles do, as part of it, have a order. So it's not a case that they rotate in just any arbitrary order. It's actually a very fixed order that they rotate in. And that's very important. That fixed order of rotation does actually have some pretty major impacts. And we are about to actually see one of those impacts, because it's going to be able to be rotating once I set a rotation speed. So we're going to go for 15, 20, and 30. So different rates for each axis. And it would help if I do this while it is not playing. So it's now going to rotate. So we can see it's rotating as we sort of expect. Then this happens. And it is only really rotating around one axis. And if I pause it, then yep, I can rotate around Y. I can now rotate back around X and Z again. But if I let it go back to running, it will again collapse. And so working with the Euler angles in this way, we experience something called gimbal lock. So because rotations in Euler angles happen in a specific order, what can happen is you can effectively fold one axis onto another, and you eliminate that axis. And if that happens multiple times, what you can result in is you've folded one axis onto another, and then you fold that onto the remaining axis. And so now we only have one axis that we're able to be rotating around, because we have folded our x-axis onto our y, and then onto our z. So that's really not what we want. And that's one of the problems with just using Euler angles, is that we can experience gimbal lock. So what I'm going to do is I'm going to set up so we can see a few different methods of rotation. And I'm going to make it easy for us to switch between them. And to do that, I'm going to use something called an enum. So an enum is a way of us creating a set of values that we give each one a name, and it's a constrained set. So in this case, the only values will be the ones that I specifically define. So I'm going to have my transform Euler angles as one of the methods. I'm also going to have one transform rotate, which will be one that we'll see is immune from gimbal lock. So I define my enum that says, well, E method is now a thing, and E method can be one of these values. Then to create that method and be able to be using it, I can say E method, and that is equal to E method dot transform Euler angles. So whenever we're referring to the values, we always do the name of the enum dot, and then we can access the values. So now I can check here and say, okay, well, if method is equal to transform Euler angles, then we do this one. So directly modify Euler angles. It can gimbal lock. Wait, is that how you spell gimbal? I have a feeling it is not spelt that way, and I am correct. It is spelt AL. Excellent. So now that I've spelt it correctly, then we can also be checking for this other method. So E method, transform rotate. So transform itself has a built-in method for doing rotations that we can make use of. So what we would do there is we would say transform rotate, and we tell it, I want you to rotate by rotation speed times time dot delta time. And what we will see is one of these can experience gimbal lock and the other cannot. So this is going to be Euler direct, going to have another cube that is going to be transform rotate. And I want to have a separate one for this, just so I can easily compare what's happening. I'll make that at minus 2.5, not 25, 2.5. So this one I'm going to say is the transform rotate. So let's watch what happens. So left is transform rotate, middle is direct Euler angles. So the direct Euler angles one has gimbal locked. Our transform rotate has not. And it won't. Transform rotate is immune from gimbal locking. So direct Euler angles, there are times where I do use them if I've got specific values I'm wanting to set in there. Usually, so I'll work in the inspector with them in code. Using something like transform rotate is usually going to be more reliable because you then don't get those issues. Now, there is a third method that we can use, which is okay, but does come with caveats. So we have this idea of a cumulative Euler angle. So I'm going to have my cumulative Euler angles, and I'm going to initially set that to however I'm rotated to start. Start at the current rotation. Just means that if I've already rotated it a little bit, that it will start at that point. It won't immediately snap. So then I'm going to check here if the method is equal to our cumulative one. And first thing we do is we update our cumulative Euler angles with rotation speed times time delta time. And then I can say transform Euler angles is equal to the cumulative ones. And build up the Euler angles over time and then set. And as we'll see, this cannot gimbal lock either, but it is not free of issues. This one we're using the built-in rotation method, cannot gimbal lock. So we're going to set up another cube, so we'll be able to see the behavior of all three. So this is cumulative Euler, and we make sure we update the method and move it to the side. So middle is the direct Euler angles that can gimbal lock, left is transform rotate that can't, and right is cumulative Euler angles, which also cannot gimbal lock. So cumulative Euler angles is absolutely a valid approach. It will work, and as we can see, it is going to wrap around there. The problem with cumulative Euler angles is over time, this value is going to get very, very large. And floating point precision is, they're not particularly precise. They only have a few decimal places of precision, which means as that gets larger and larger, it's actually going to jump larger amounts with those angles. So it's not really an ideal approach. So in terms of which methods to use, if you're needing to be continually rotating something, I would be using something like a transform rotate. It's going to work far more reliably for you. If you are just setting a direct rotation, then Euler angles can be okay. We'll be seeing another method in a moment as well that we can use for that. If you've got stuff that's rotating over a time period, but that's a very constrained set, you could use cumulative Euler angles. But it's generally not ideal. I would say for most cases where you're rotating stuff, make use of transform rotate. It's going to be the most reliable method. You avoid gimbal lock and you get the behavior that you're after with it in terms of it continually rotates and you can rotate it by whatever amount you wish. So, okay, that's rotation. Related to that, we often want to have something look at something else. So let's set up a scenario where we can do that. So I want to create a cube, and this is going to be my camera mesh. And I'm going to bring this up so that it is here on the corner. So it's going to be there. Let's change the scale of this a bit so that it is more sort of a camera shape. So that's pretty cool. But if we see when it rotates about that pivot point. Not really ideal. We want it to be pointing at the particular thing, which, yes, it could do with that, but we don't really want it to be pivoting around the middle. We want it to be pivoting from one of the ends. So an easy way to do that is I've got that object, I create an empty parent, and this is my actual security camera. And then what I do is that mesh, I offset it. So with offsetting it like that, now I have my camera that wherever I rotate it, it's rotating around a much better pivot point. So that's pretty cool. That works. So we've got our security camera and we've got our mesh. We need a target object to be looking at. So this is going to be our camera target, which I'm just going to position in the center there, like that. So that's cool. So the camera will be following that. And just for good measure, I'm going to actually move my main camera here so that my main camera is linked to this. So that the idea being that the camera can just zoom around as the object actually changes. So again, we just get that positioned. So now my camera is right at the front of it, which is good. So wherever that faces, we can rotate that around a little bit. Wherever that is facing is what we're actually managing to pick up on our game view. So that's cool. So we need this to be always pointing at the camera target. So let's set up our look at script. So this is a demonstration of look at. So one of the key things we know we're going to need for this is when we need a transform of our target to look at. We are also going to have a bunch of methods for how we can do this. So one of the methods is that we're going to be doing some vector calculation. So simple vector math version. So again, we set up our variables so we can control how this is working. So our method is a method simple vector math. So let's look at what this looks like. So what we can do is we can take our target and we can get its position and we can subtract our position. And that, if you remember, that is giving us a vector that looks from our location to that target. So it's a vector from us to the target. And if I normalize that, I can actually just say, well, transform dot forward is equal to that. So the method is simple vector math. And we just use by changing the forward. Change our forward to point at the target. So transform has things like forward and up and right. And not only can we read from them, which is super handy, we can actually just directly set them. And it will work out how to orient the object so that that actually is pointing where we need it to be. So let's take a look at what happens with that. So we've got our security camera. We put on a demo lookout script and we give it our target. So if we run this, and I'm going to select the target, then as I move that target around, camera just nicely moves to follow it. So a really easy way of having something always be facing to look at a particular thing. So that's pretty cool. There's different ways of doing this though. So the other method is we have a transform look at. Because just like how transform has a rotate option, we also have a look at one. So if the method is equal to transform look at, then we can say transform look at, and we give it our target, and we give it what we want it to use as its sense of up. So in this case, vector 3 up. Use the built-in look at method. Let's see how that behaves. We should see essentially the same result. The main difference is that it is allowing us to set what the sense of up is. So our security camera, we want to switch to transform look at. And then we'll again move the target around. So again, yep, it's behaving how we would want, which is cool. Let's see what happens if we change this from being our up direction to right. I haven't tested this before, so we're going to find out what this looks like when we do this. And that kind of makes sense. That we are now, oh, that is so disorienting, trying to move it while watching the game view. So we can set what our sense of up is for it. We're going to not go for it being that. We're going to stick with the actual vector for up. So that's cool. We can do it using vector maths. We can do it using transform look at. We might not always have transforms. So we also have another option called Quaternion. So Quaternions are a way of working with rotations, and they're an alternate method. And I use Quaternions a lot for when I am doing stuff like this, where it is stuff where I'm rotating cameras and wanting to apply transformations based upon a rotation to a camera. That's something Quaternions are really great at. So what I can do is I can say with a Quaternion, I want to get a look rotation, and I can give it the forwards vector, which conveniently, we already have our forwards from up here. And then I can also give it vector 3 up. So then I can just directly set my transform rotation like that. So use the Quaternion look rotation. So transform look at is great when we've got transforms that we're working with. That makes it's a really easy method for that if we're specifically just wanting to directly rotate the object. Otherwise, we need to use either a direct vector-only based approach. We could override things like forwards, or we can take stuff a different setup where we can use Quaternions, and that gives us a rotation that we could use on a transform, we could use with launching a projectile. The Quaternion approach would be the one that I generally recommend going for, in that it allows us to explicitly set what we want as our up direction. So transform look at if you're working with transforms. Otherwise, Quaternion look rotation if you need to be doing further things with it. So the cases where I might use a Quaternion look rotation rather than a transform look at is if I want to get that rotation and then I want to do something further with it. So for example, if we want our camera to slowly rotate to that, then a Quaternion look rotation gives us our destination rotation, and we can be merging towards that, which that's something we will take a look at as, I think, a fourth method, once we've made sure that the Quaternion look at one works. So we want to make sure we've actually got this working properly. So Quaternion look at, and I'll grab my target. So at the moment the camera moves as fast as the target moves. which could get really disorienting for players. So we kind of want to have a smoothed version of that rotation, and this is where the Quaternion look rotation in particular comes in handy. Doing a smoothed rotation with Euler angles, things like that, is doable, but it's so much easier with the Quaternion look rotation. So we'll be able to take a look at that in the next thing that I'm going to be adding in. Okay, so we want to have a smooth look at. So we want to have Quaternion smooth look at. So method is going to be Quaternion smooth look at. So what I can do is first, similar to this one, I'm going to calculate the look rotation. Target, actually desired rotation. It's going to be that. So I'm working out desired look rotation. But then I need to smoothly move towards that. So what I can do is I can use a Quaternion, and then we've got a rotate towards. So I give it my current rotation, transform rotation. I give it my target one, which is the desired rotation. And then I can tell it how fast I want it to be able to turn towards it. So what I can say is we float, and this is going to be rotation speed. And I'm going to make that maybe 30 degrees a second. So rotation speed multiplied by time, delta time. And I can then, again, similar to what I had before, if I just directly set that. So transform dot rotation, and then rotate towards the desired rotation. This allows me to have the camera, what I expect to see with this is that it will smoothly rotate towards that target one. So let's make sure we have switched our security camera over to smooth look at. And then you can see it pans down. And then as we move, it pans over to look at it. And the advantage with the Quaternion is it can do this really smoothly. Euler angles, it's a lot harder to get a really smooth rotation, especially if you're doing things like flipping over to the side here directly behind it. A Euler angle version is often just going to flip upside down, not necessarily what we want. Whereas the Quaternion version, it's a lot easier for having it just rotate smoothly, and that's because we're preserving that idea of, well, we want to be looking up. So it's not going to rotate it to ridiculous angles. So, okay, different ways of working with rotation for stuff when we're having something look at things. We can do it directly vector-based if we're not wanting to worry too much about whether it might get rotated, whether it gets a wrong sense of up. We can use transform look at if we're directly working with transforms and we wanted to instantaneously look at the object. We can use Quaternion look at, or look rotation, if we're wanting to, again, preserve that aspect of having it looking the up sense, and that we still use that forward direction. And we can directly set rotations, but the main reason why we often use stuff like the Quaternion version is so that we can smoothly rotate towards it, or so that we could apply an offset to it beyond our current rotation. So Quaternion-based method is generally what I would use if I am working with cameras in particular, stuff where I'm doing more complex rotations and I want that movement to be really smooth, really precise. Quaternions are my go-to there for that. But otherwise, I would generally use things like a transform look at if I don't need it to be smoothed over time. If I just need it to be an instantaneous thing, I would use a transform lookup. So okay, we can do a lot with rotations. We've previously seen stuff with things like scales and things like that. We want to have a look at how can we have something move towards something else. So I'm going to create let's create a floating cube that I'm going to position here. That's a decent spot. And this, I'm going to make it seek a particular target. So I'm going to set up another script, and this is going to be a seek target. And again, we'll have different methods of working with this. But key things that we know we're going to need. We know we're going to need a transform for our target. So let's look at different options. Simplest option is, and we've seen this a bit before, we get our target our target position. We get our position, and we can normalize that. And this is going to be the direction we'd go to move in. So the simplest version we've seen of this is our transform.position, and we add in this direction vector multiplied by, well, we need our speed, so it'll be a float, our movement speed, let's say it moves at 1 unit a second. So our simplest version of this looks like this. And I'm going to, again, set up another enum. And you'll notice all these enums have the same name. That's because they're within different files, different classes in particular, so they're effectively separate things. So this is simple transform position. And again, we set up our variable for that. Method is equal to this. So I'm just doing this early on because I know I'm going to have a bunch of methods for this. So if our method is eMethod, simple transform position, then we just move towards the target. So okay, that seems reasonable. But let's see how this looks and how it behaves. So our camera target is what we're going to head this towards. We've got our seek target. We're going to make the destination one is our camera target here. Makes it a bit more dramatic, seeing as the camera will be following it. So okay, just heads towards it. And that needs to be so much faster. But this is actually a really good example of, well, it's just oscillating like madness there. It's just bouncing all around. Not ideal. And if I set it as a really low value, we could avoid that. But we want to look at other ways of doing that. So this is just move based on vector, direction vector. So it's not ideal because it will bounce around like that. So we can also have using move towards. So move towards, we have a look at what that does. Method fits using move towards. We can say, hey, transform position, I want you to be a vector 3, move towards. So use your current position. And I want you to move towards the target position. And I want you to move movement speed by time dot delta time. So that's actually the maximum speed using move towards. So this is the maximum distance that this will move. It will not move that amount unless it needs to. And we'll see that we get quite a different behavior with this. I'm going to seeking cube. So if I change its one to be moved towards, then we watch how that behaves. So it heads towards it, gets there, and you notice we don't get oscillations. That's because move towards, the amount we tell it to move by is the maximum amount it will move by. If it doesn't need to move that full amount, it will move less than that, and it will and so it will not overshoot, things like that. So it's a really effective method for having movement where it will just move there and it stays there. If we're just using transform position, it's less than ideal because it ends up, we have that problem where it can jitter at the end. But if we notice when this is moving, it doesn't rotate. So it's not trying to arrive with any particular direction, things like that. So we can make this better. So using direction. So what we can do in this case then is F method is using direction. Then we can combine some of our earlier stuff. So what we can do is we can say, well, transform, look at our target, and we can maintain the sense of world up. So turn to face the target. And then move towards the target. So we can instantaneously face towards it, and then we move directly towards it. So move directly. I'm going to directly towards the target. So this way it should face it and then moves towards it. So it should always be arriving with the same face pointing at it. To make that a little bit easier to tell, what I'm going to do is I'm going to just chuck in another cube. This is going to be the nose of the seeking cube, and I'm going to shrink that down. And I'm just going to move it so the forwards axis, just move it about 0.5. So we've got it poking out a little bit. And I'm going to give it a material with a different color. So the nose, let's give it a magenta nose, because as any developer knows, nothing is ever wrong when something is magenta. So, okay, that was what happens if we just use move towards. If I now change it to use direction, and then we watch. So it faces it and heads towards it. Cool. Be nicer if it rotated smoothly towards it. It might mean that it takes a bit more of an arcing path, but it would work. It would look a lot nicer. So we can have float rotation speed using smoothed rotation. So our final method, and we're combining a bunch of things from our two earlier ones. So FR method is equal to using smoothed rotation. And the first thing we want to do is we want to smoothly rotate. Now, I am shamelessly going to steal my code from the demo look at. And again, copy and paste, it's a really useful thing. I'm not going to try and claim that I never copy and paste, because I totally do all the time. So that's pretty cool. We've worked out the rotation. It will smoothly rotate towards it. Now this one is close to what we're after. This one moves towards it, but we don't want to be moving based upon just, if we just moved directly, what would happen is it would look like it's sort of sliding. the rotation would look off. So what we actually want to do is we want to move based upon our forwards direction. So what we can do is initially I'm going to say, okay, well, transform position. I want you to add to that the transform dot forward, so whichever way it's currently facing, times by movement speed multiplied by time dot delta time. So this is going to jitter. We know that it is going to have that jittering at the end, but the key thing is we're using whichever way we're currently facing. And that's the key aspect of this. If I just use this version, I'm focusing on moving our center point, not moving based upon how we're facing. Whereas I want to have it be tied into how we are actually facing. So if I use smoothed rotation, what we should see is it's a bit of an arcing path that it takes because its rotation rate is fairly low. So this is something where generally for a character, going to actually want a much higher rotation rate than you might initially think. So it's going to rotate around and heads towards it, but then it's going to have this problem where, yeah, it can overshoot, it can end up looping around it. So that's something where what we can do is we could check how far away we are from it. And so what we could say is if we're really close to it, we switch away from using like of this. So we could have something like a arrived threshold, and that's going to be 10 centimeters. So we could say, well, f vector 3 distance, so the distance between our position and our target position, if that is greater than our arrival threshold, then we use the direct move. We use this movement approach where it's sort of smoothing out. It's based on the transform. And otherwise, we take the direct approach. So what we're saying is if we're farther than arrived threshold away, then use smooth movement. Otherwise, move direct. Let's take a look at how that now behaves. And we might need to adjust the arrived threshold a bit there, we'll find out. So it's heading towards it and stops, it's still doing its bit of rotation. So we could actually make it that the rotation side of things here also doesn't happen, except when we're a bit of a distance away. So we can bring these down here, like that. And then we bring this one up. So this we are moving based upon how we're facing. Move based upon how we are facing. So that should give us a nice combination there of it's going to rotate as it's moving, and it does take that bit of an arced path, gets there, stops. And we could, as we mess with different things like the speed, in terms of the movement, the rotation, we'll be able to get different effects. Once it's actually there, I'd be able to do things like having this move, and we can kind of just lead it around. So really easy to have something where it's smoothly moving towards where we're at by rotation, and we can see our camera is smoothly following it as well, so we can combine these different elements. So just recapping the different things. Rotations. We often want to use transform rotate. If we're doing a continual rotation for something, transform rotate is the way to go. We can directly work with Euler angles. but we need to be mindful that gimbal lock is a thing that can occur there. And if it does, that creates an issue that we can't easily recover from still using Euler angles. So transform rotate is generally going to be your best approach. We can make something also rotate to look at a particular thing. And how we do that depends upon the kind of effects we want. If we want it to just point at it and we don't care about whether it gets rotated, it's just pointing facing that, we can just work direct with vectors. If we care about what we want is its sense of up, and we are working directly with transforms, and we want it to snap rotate, to immediately face it, we can use look at on the transform. If we don't have transforms and we want to take it a bit of a step back, we can use Quaternions, which if we're using Quaternions, that allows us to then have it smoothly rotate towards it, which can give us a much better effect. And then we can combine all of those things for when we have something moving. We can move again by directly changing position, but using the direct position changes, we can get jitter, and we almost certainly will get jitter. If we want to avoid jitter, we can use move towards, but that just moves the object directly there. It doesn't make it face where we're heading. We can then do the naive approach of where we look at the thing and then move towards, and that works. But it's a snap rotation. If we want to have something smoothly rotate, then we can go for the approach of, again, using Quaternions and rotating towards that, and then we use our forward facing. But we often need a threshold. So once we get close enough, we switch back to a more deterministic set of movement where we're just directly moving our position there. Otherwise, we can end up continually looping or having jitter on that location as well. So this is going to give you a lot of different methods of how you can move things in your game. If you want something that's chasing the player, for example, you can use some of these methods there for that. And as always, the key with these is to dive in and to experiment. See what other things you can create with this. We've got a camera set up in that here. We've got the deep dives talking about cinemachines. This is something where you could take a look at the cinemachine setup, and then you could have some stuff there where you've got characters being chased and you're switching between different camera views. Lots of different cool things you could do there. So dive in, experiment with it, see what kinds of cool things you can set up and get up and running with that. Thanks folks, that is all for this video. If you're looking for the project, you'll be able to find it up on GitHub, and I've put a link to that in the description below. If you've got any feedback, any questions, please chuck in a comment. And if you're looking to find ways to support the channel, chucking in a like or subscribing to the channel is always a big help. If you're looking to go further than that, then I do have a Patreon set up, and any support there is super appreciated. And there's a bunch of different things that you'll get as part of being a patron there. And the big thing is it's going to help me make more cool things like this, which is going to help more people like yourself to be making more games, which is awesome. And that is all for now. Thank you.